48. So 48 is figuring out the net torque on this strange bean-shaped object. Net torque is like the net force. If you have three forces acting on something, an object in multiple directions, then you need to find the components of those forces in the x and y, add the x's, add the y's, all that stuff. With torques, it's slightly different because there's really only two ways that the torque can act: clockwise or counterclockwise. And you'd use the right-hand rule to. We're going to do that more next chapter, in chapter 11, with the right-hand rule for torque. But just a little preview: you can use the right-hand rule to figure out the direction of the torque. And just to give you, again, to enhance that preview, let me draw the object here. Sort of. I guess it's kind of like the object. And the center of mass, or the pivot point anyway, at least, O is here, B is here, C is here, A is here. So if it rotates this way, you take your right hand, curl your fingers around in that direction, and your thumb should point into the page. So we'll say into the page is negative, so this way, rotating this way is negative. And if it rotates that way, take your fingers, curl them around that way, your thumb should point up out of the page, and so we'll call that positive. We'll call counterclockwise positive. Anyway, so this force at A is acting up that way, which is not perpendicular to the radius, or the direction from the pivot point to where the force is acting. To get maximum torque, you need the force perpendicular to that radius, right? So any vertical component, any component parallel to the radius, does nothing. It's like trying to open a door by pushing straight into the hinges from the edge of the door. It's not going to work. So all you need to do is find the component, this I guess perpendicular component of this force. And as you can see, that is a cosine. If you make a triangle here, that's a cosine. So if this whole big angle is 135, then you do 90 minus that to get this little angle, which is 45. Theta A equals 45 degrees. Object C, force C is acting sort of this way, and the radius is that way, so perpendicular to the radius would be like that, sort of. I'm not going to erase. It's like that, I guess. And then here's the parallel component. So we need this angle. If this whole big angle, according to the book, from here to here is 160, we do 90 minus that, and that gets us theta C equals 70. I'm not labeling here 70 degrees. I'm not labeling all of the little points because I feel it's going to get cluttered, but you can just look at the book to see what I'm doing. So, and then, awesomely enough, force B is perpendicular to this radius, so we don't have to do anything. Just do, like, this actual force is completely contributing to the torque. So as you can see, this force causes a torque counterclockwise. It wants to rotate it that way. This one, that's A. B wants to rotate it clockwise, and C wants to rotate it counterclockwise. So A and C are acting in sync together, and B is fighting against them. And according to our convention here, the torque due to B is negative, and the torque due to A and C are positive. So we'll say torque net is torque A minus torque B plus torque C, right? And torque is force A times the distance, the radius, which is this distance, but it's actually not force A, because force A is this. We want this component, so we're going to multiply that by cosine of this angle, 45, minus force B, RB, and force B is perpendicular, so we get the entire force contributing to the torque, so we don't need to take a component of that, plus force C, RC, and this component of force C is cosine of 70. And yeah, so now we can plug in. So force A is 10. You can look in the problem to see that. This distance here is 8. And cosine 45 minus force B is 16. RB is 4. Plus force C is 19. RC is 3. Cosine 70. And that equals 12.1. It's positive Newton meters. So the positives win, so it's going to rotate that way, counterclockwise. And that's it. Net torque. Alright. Bye-bye.